All right. Probably only going to get one more in. So what we just did here is an example of power series. Remember I said that you have to know chapter 10 to do chapter 11? Do you see it now? Yeah, you have to. No way to do chapter 11 without knowing chapter 10. All right, here we go. We got the sum as k goes from 1 to infinity. Of x minus 2 to the k power on top over square root k on the bottom. The numerator, x minus 2 to the k, might prompt you to think about using the root test. Although the denominator, square root k, imagine doing the kth root of square root k. That's going to be a problem, isn't it? Yeah, that denominator will cause us a problem with the root test. So we're going to need to use something different. And it's going to be the ratio test. So for the ratio test, r equals the limit as k goes to infinity. Absolute value. And put the k plus 1 term on top, so that's x minus 2 to the k plus 1 over square root k plus 1 over the original. And when we divide fractions, we multiply by the reciprocal. Absolute value is still there. Alright, so I'm going to begin showing fewer steps than I was showing in chapter 10 on some things. Like here, x minus 2, the bases are the same, so we subtract the exponents. K plus 1 minus k is just 1. So we have x minus 2 to the 1 power on top, which we'll just write x minus 2. Times, actually I'll put it in parentheses, times this square root k over k plus 1, we can write that under a single root. Like that. Any questions there? All right, the expression inside the root, k over k plus 1. Where does that go as k goes to infinity? Here. That's a first degree polynomial over a first degree polynomial.
Unless it goes low, doesn't it go to infinity by the way?
No, you're thinking too much.
1.
Yeah, 1, the ratio of the leading coefficients.
Oh, yeah.
1. All right. You're making it really hard. You could use L'Hopital's rule. I wouldn't want to, but you could. Okay, so this equals 1, so we have the limit as k goes to infinity of absolute value x minus 2. X relative to the limit is a constant. The variable of the limit is k. So the limit of a constant is a constant. So this equals absolute value x minus 2. Now remember, we're looking for what values of x make this converge. Some values of x make it converge, some don't. Okay? So the ratio test converges when this limit is
Less than the value of x minus two.
what's it say on the sheet? Less than 1.
Oh,
Yeah, you're making it hard again. Less than 1. So converges when absolute value x minus 2 is less than 1. Now go back to algebra. Many of you did this in 8th grade. Put that between -1 and +1. And solve it for x. And 1 is less than, x is less than 2. Oh, I'm sorry, 3. I did that in first grade. So we know that it converges for everything between 1 and 3. We can actually determine the radius of convergence right here. The radius of convergence, capital R, will be 3 minus 1 over 2. 3 minus 1 is 2 over 2 is 1. Yes, there we go, 1. Radius of convergence is 1, so the value in the center here is 2. You go up 1, that hits 3, down 1, that hits 1. So that's your radius. But we still don't know about the endpoints, do we? Because if we put either the endpoints 1 or 3 into here, when we do the limit, if you put in 1, you can go all the way back to here. If you go put in a 1, 1 minus 2 is -1, that limit will equal +1. If you put in 3, 3 minus 2 is 1, absolute value of 1 is 1, it equals +1. So either of these endpoints make the ratio test, the limit for the ratio test 1. And the ratio test is inconclusive at 1. So now we have to plug in our endpoints here and run a chapter 10 test to determine if it converges or diverges. All right? So endpoints. I'm going to put in, I'll start with the one on the left, 1. X equals 1. So go to our original sum. K equals 1 to infinity. 1 minus 2, well, we'll write it out so we know what we're doing. Normally I would just write -1 there. So that equals the Now, if that -1 was not up there, if it was just 1 over root k, we could use p series. Because square root of k is like k to the 1/2. So p would be 1/2, and we would say it diverges. That's less than 1. But we have that -1 there, so this is an alternating series. So let's use the alternating series test. And so using the alternating series test, we do limit as k goes to infinity of 1 over square root k, which is going to be 0. And what does the alternating series test tell us then?
Value converges.
Converges. So converges by alternating, I'll abbreviate, series tests. All right, now let's check our other endpoint, which, looking back here, is 3. Go back to the original. We have the sum as k goes from 1 to infinity of 3 minus 2 to the 1 to the k power over square root k, which is like, I'm going to write it as 1. So that'll be 1 to the k, which is always 1, and I'm going to write square root k as k to the half. What test should we use here? P-series. And P equals 1/2, so it diverges by P-series test. So back to here, we saw that it converges at 1, diverges at 3, and its radius of convergence is 1. So here's our, I'll write the final answer here. Interval of convergence because it converged at 1, we're going to get a bracket there to include it and a parenthesis on the 3. And then the other part that Pearson's going to ask for is the radius of convergence. Is capital R equals 1. All right, any questions? Yes, sir.
So basically, anything below 1, would it like converge or would it diverge or?
It's a diverge. You put in 0, you're going to have negative 2 to the k. So that numerator, negative 2 to the k, is going to keep growing. Negative 2 to the 1 would be negative 2, squared would be 4, cubed would be negative 8. That's going to grow faster than this, and then it's not going to converge. If you put a number greater than 3 in there, put in 5, 5 minus 2 is 3, so then you're going to have 3 to the k, and that's going to outgrow the denominator, and it's going to diverge. It only converges for values from this interval. Put anything from that interval in for x, and this will converge. Does that make sense? That's what this shows. Let me look here. We'll do more examples on this on Wednesday, but you have enough to get started now. So in 11.1, which is due on Thursday, we studied Taylor polynomials. We're taking a little break from Taylor, and we're looking at these power series. In 11.3, which we're going to finish this on Wednesday, I don't know if we'll start 11.3 or not, but we might. 11.3, we're going to start studying Taylor series. So 11.1 was Taylor polynomials. It was a finite number of terms. Taylor series is an infinite number of terms. And after we get that under our belt, I'm going to show you the most amazing thing. It's just incredible. All right? So stay with me on this stuff, okay? The most amazing thing is coming. Have a great